So this talk is really going to show some of our first results and the work that we've been really starting to get ground in, no pun intended, regarding electrostatically charged dust grain interactions with phospholipids, which are a type of biomolecule. So my main collaborator on this work is my PI, Tom Orlando. But really, this work has been funded and moved forward through the NASA Solar System Exploration Research Virtual Institute, or SERVI, who awarded me a NASA postdoctoral fellowship to work on this here for a couple of years. So this is an image of a dust storm on Mars, right? And like I was saying, we know that dust storms on Mars are super dangerous, right? This is from the Martian. I thought it was super appropriate since we just got done hearing from Lisa, and you know that this is a scene from the movie The Martian. And those of you that know this scene know that this is probably the least scientific part in the entire story. But nevertheless, Mars is definitely full of dust. Those who attended the talk last Friday noticed that dust is an issue for the Mars instruments as well. I got interested in the dust problem more as a function of what was going on the surfaces of airless bodies where there is no atmosphere. This being an image of the Apollo astronauts trekking along the surface of the moon. Clearly, there's a lot of dust there. And in fact, the dust on the moon was cited by the Apollo astronauts as probably one of the most significant challenges to human exploration. And this dust can be very irritable to biologic tissues. The astronauts noticed that they could get it into their lungs. It caused them to have lung irritation. It could get into their eyes and cause eye irritation. And of course, inhalation of fine particles is a well-known risk from Earth-based environments, such as in mines or in demolition work. And really, we're curious, though, because the atmosphere or the environment of airless bodies presents very new challenges that aren't encountered in an Earth environment, such as the grains can become electrostatically charged, and they're irradiated by solar radiation, which can cause perhaps a more reactive grain surface. So the idea behind the project that I'm going to talk about today is to study the effects of electrostatically charged grains when they come into contact with biologic molecules. The first step is to prepare thin films, and when I say thin, I mean on the order of a few molecular monolayers. Thin films of these molecules on some smooth substrates. And then step two, independently of step one, is to get these grains electrostatically charged under high vacuum conditions. And then finally, the third step is to bring those two facets together and bring those electrostatically charged dust grains into contact with the biomolecule films and look at what changes are caused in those films as a result of that exposure. So just a sort of couple images of what the project looks like. It's a little vacuum chamber that I built up in the lab. And the image in the center here showing sort of the design where you have a little dust cup and then you can set your sample underneath of that dust cup. And so then the grains within the dust cup become charged and then you can drop them onto the film below. And I show that in a little bit better detail here. So on the right, you can see that there's this little pile of dust in the cup. And that cup actually has a series of little holes in it. Those holes are just a bit larger than the grain size. And so then we can actually vibrate that cup using something that is basically just a magnet. And so we have a coil, which is a coil of wire, which we then put a signal into, and so that's basically just an audio signal coming in. And then around that coil of wire, there's a permanent magnet. And then by driving that oscillating current within the coil, you can get that that coil to jump up and down, shake that dust. And so you see the sample holder can bounce up and down, shake that dust, which can then fall through and onto the films below. So what films are we talking about? And so we chose to use Dipalmytoylphosphatidycholine, or DPPC. So DPPC is a phospholipid. It's actually a very common phospholipid. It's a major component of human cell membranes and is particularly a common lung surfactant. So you find a lot of DPPC within your lungs where the astronauts said they were getting that irritation. And so if this molecule is susceptible to these electrostatically charged dust grains, we're hoping to see that. These molecules, as a phospholipid, they have a hydrophilic head and a hydrophobic tail. And we can deposit them onto our surfaces using Langmuir-Blodgett deposition. And basically all Langmuir-Blodgett deposition is a technique where we take these molecules, we deposit them onto a water trough or a bath of water, and the molecules, since they have a hydrophilic head, they self-orient, right? And so the head is attracted towards the water, the tail away. And then by slowly closing a barrier, what we can do is we can compress those molecules on the surface. So as those molecules are being compressed on the surface, they self-order. And then by drawing a substrate through that film, we can then deposit those molecules onto the surfaces, ending up with our nice little bilayer films. Here's an image of some of those films that I took using atomic force microscopy. You can see the blank silicon film, pretty blasé, featureless. The deposited films have much larger islands, and you can see that we're getting quite a bit of DPPC deposition onto our samples. So then the next phase of this is to get these grains electrostatically charged. You might be aware that electrostatic charging of grains or fine particulate matter is actually pretty common. You may have seen pictures like this one here before, which shows a discharge or lightning within the plume, the column of a volcano, and this is caused by these grains rubbing along one another, becoming electrostatically charged through Triboelectric charging. And so those that are familiar with Triboelectric charging is pretty common. It's what causes the balloons to stick to our hair or to a wall or what have you, or the electric shock from rubbing your feet along the carpet. So we wanted to try and do this in a controlled setting with grains that are representative of a body like the surface of the moon. And so here's a video that I took showing the cup where I'm starting to vibrate these grains around. Now this cup that I'm showing here doesn't actually have the holes in it. We wanted to just see if we could get these grains charged without dropping them down first. So what we actually did is we installed a sample of conducting polymer, which is actually being developed by my PI and collaborators as a potentially conductive spacesuit material. So we thought if we can get the grains to jump off of this conductive spacesuit material, well, then maybe we can minimize some of that grain sticking like we saw in the picture earlier, which can cause degradation of that spacesuit. And so you can see here the grains are vibrating around, and every once in a while, it's maybe a little hard to see in this video, but you can see the grains start to jump out of the cup. And so what we're doing is we're applying a potential to that surface of that conducting polymer. And since the grains are becoming electrostatically charged, the ones with the charge opposite the voltage that we're applying to the conductive surface are pushed away. And so the cup vibrates along, and I'm actually going to skip forward to where it gets really exciting here. And all of a sudden, we see that some of these grains, there's just a huge reaction, and they fly off of that surface. And so what we're showing is that we're definitely getting this vibratory electrostatic charging of dust grains, but we can also sort of push them off of this surface simply by applying a potential. Another experiment that I did that is not really relevant to the Earth environment, but you could see maybe what this could look like. It's something more along the lines of a Martian pressure. I will note that this is not a Martian composition. This was very much just to test sort of experiment, just to show you sort of the effects that can happen when you get this electrostatic charging of dust grains. And so right there, we see that we applied the potential to the surface, and what you get is this massive discharging and actually a plasma forming above that surface due to the large amount of electrostatic charging of those dust grains. And so you can see this is a really high potential. You wouldn't probably just apply this to a spacesuit. You'd have to do it in a much more controlled manner. But you really see that there's a lot of charging on these dust grains, and we can get them to interact strongly with these spacesuit materials. So just real quickly, in the minute or so I have left here, what did we see when we dropped these dust grains onto the DPPC? So you can see here we've done a few experiments where this is the sample before, this is the sample after. I don't have a very good video camera, so it's kind of hard to see in live time. It takes a few minutes. But we're definitely getting these grains to drop onto our samples. Sometimes we get a lot of grains dropping onto our samples. And the technique that I'm going to talk about real quickly that I use to analyze the effects caused by these dust grains is called XPS, or X-ray photoelectron spectroscopy. And what this technique allows us to do is use X-rays to eject electrons from 4 levels of the various elements in our sample, and in particular from the uppermost several monolayers of our sample. And so only those regions that are almost certainly coming into contact with dust grains. Then, depending on the energy of those ejected electrons, we can assign the various peaks in the envelope to specific molecular bonds. And what I'm actually showing is a before and after, where the black is unexposed, the red is exposed, and we don't see very big changes in between those two. So with the XPS technique, maybe it's not super clear, but we are pushing forward, trying to determine if there's a better way of looking at how these grains affect these molecules. So moving forward, the initial results show that DPC is at least not strongly affected by these dust grains, although there's still some work that we're doing to look at this. In the future, we're hoping to better quantify how electrostatically charged the grains that come into contact with the films are. That just requires measuring basically the charge on those grains, and then doing additional characterization post-exposure using AFM, and also using other techniques such as infrared spectroscopy. And certainly we see that we can get these dust discharge events, and we're looking into different ways of looking at those using fluorescence microscopy, perhaps as a way of being able to, in that discharge vapor, determine some sort of chemistry that's happening.